Uh, Hello guys, welcome to another discussion. In today's discussion we are going to look at differential equations. So basically, maybe for a start we'll go for the definition of a differential equation so that we understand what a differential equation is. So basically, to define a differential equation, we are told to say a differential equation is an equation that involves an unknown function, let's say y of x, and its derivatives. Okay, so meaning those derivatives that are going to be involved are the derivatives of the function y of x, even though it is not known. So here's an example. So what we have here is the second derivative of the function y plus 2 times the first derivative minus 8 times the function y itself. So what you have here is an example of a differential equations, a differential equation. So you'd find that these derivatives can go in as much as they can go up to 3, 4, they just any natural number can obtain such derivatives. And then here we have what is called a solution. What is a solution? A solution is the function, let's say y of x, that satisfies a particular differential equation. So look at what you have here. If you have this as your differential equation, then the solution to this differential equation would be the function, let's say y of x, like that. Then we can verify to prove or to check whether this function y of x here is the solution to this one. So we can start by saying, so I say example. So the example that we are looking at is the function y, which is equal to e to the power of 2x, like that. And then our differential equation is the second derivative of the function y, the first derivative, and the y itself. So to do that, we are then going to need, the first thing that we need is you can first of all obtain the first derivative. So we are saying the first derivative, which is dy dx of this function, it is 2e to the 2x, like that. This is the first derivative. And then the second derivative, let's say, so obtaining the second derivative, you can only obtain the second derivative based on the first derivative, like that. So meaning it's this that gives us the second derivative, which is then going to be a 4e 2x, like that. So at this point we have the first derivative, the second derivative, and the function y itself. And then you can try and plug them in here to see whether what you have this side will equal to 0. If this is not equal to 0, then the function y is not the solution to this differential equation. But if you get a 0, you're then going to say the function y is the solution. So let's get our second derivative here, the first derivative, and also the function y as it is here, and try to plug it in there. So I'm going to use a different marker here so that we see something. So what we have here, we are saying the second derivative, let's just do this, implying that the second derivative, which is this, which is say 4e 2x, like that, plus 2 times, so we're saying 2 times of the first derivative. So multiplying this by 2, that would be a 4. So if I want, I can write it like this. Then you are saying minus 8 times the function y. So y is what you have here, which is e to the 2x, like that. So what you have here, if you compute it properly, you discover to say that you are then going to have a 4 plus 4, like that. And then 4 plus 4, that's 8. So at this point you're going to have something like 8 minus 8. So you can have it like that. Okay, this side you're going to have 8 2x, and then minus this one 8e 2x, which is equal to 0 if you work it like properly here. So at this point you're then going to conclude to say this function y is the solution to a particular differential equation, like that. So basically there's a few things that you need to understand. So basically that's how you go about a differential equation, and then the solution, like that. And then from here, maybe a few things that I would need to mention we know to say what we have here, since we are told to say a differential equation is an equation that involves an unknown function and its derivatives. So there are two types of differential equations. Just clear up some space. So I mentioned to say there are two types of differential equations. That's to say the first one is so we have the ordinary and also the partial differential equations. How do these two differ, or how are they different? The ordinary differential equation is such that it's just like what we had. We had something like this. This is what we had for the, and we would call this one the ordinary differential equation. So this is an example of an ODE. And then the partial differential equation. An example of a partial differential equation is an equation that comes in this form like this. Let's say y. Maybe you can have it, let's say. Okay, so we assume something that looks like this. This one is what we would call a partial differential equation. How are these two different? These are different in the manner that this one is a function. So what I'm going to have here is going to be some function, let's say f, that will depend on two variables. That's to say this one depends on t and x. So this is an example of a partial differential equation. So in as much as you are differentiating this one, you're going to differentiate it partially such that you need to have the partial derivative of the function y with respect to t, and also the same function y can then be differentiated with respect to x. So meaning you are differentiating this one partially. You can have more than 2, 3, 4 variables like that. And then this one is an ordinary one because it only depends on x, or it fully depends on x. So those are just two types of differential equation. You're going to have partial and also an ordinary differential equations. Okay, so from here we'll then focus on the ordinary differential equations. So differential equations can then be classified according to certain properties that we are going to discuss here. So what you have is that the first one, which is the standard. So we have what we call a standard equation. So we're going to have something like a standard I hope the spelling is correct. So we have standard equation. So a standard equation is one that looks like let's say dy dx is then equal to, we are saying it's a function of x and y. But then this function may not necessarily be of x and y. It can just be a function of x like that. But then this is what you're going to get as a standard differential equation. So the first one is a standard. And then we have something like a linear equation. So a linear equation is one that looks like dy dx plus z. We're saying p as a function of x multiplied by y, which is then equal to q of x like that. So p of x is some function of y, x, and also q is another function of x like that. So what you have here, this is a linear equation. And then we also have something like the third one, or the one that we are going to consider as the third one, the Bernoulli. Bernoulli equation. So the Bernoulli equation is one that looks like saying dy dx plus p of x multiplied by y being equal to q of x. Then this is then multiplied by y the power of n. Now here we are saying where n is not equal to 1 or a 0. So at this point we would not have n raised to the power of 0, because the case we are going to have n raised to the power of 0 to then be a linear equation, and then we can't have it as a power of 1, meaning it's some other number greater than 1 going upwards like that. Okay, so here we have 3, and also we have, I don't know if the space here is enough. So we have the other one that we call exact so of exact equation. So I'm just underline this. Okay, so the exact equation is such that it is an equation, let's say so what you have here, this is an example of the exact equation. So it is such that if you rearrange the standard form like this, you are going to have something like this. But then to verify or to check whether or not the given equation is an exact equation, you'd need to check. So you are taking the partial. So now what you have here is that you have to differentiate this one partially. Let's say m is some function of x and y. So you need to differentiate m with respect to y, and then what you get should be equal to a case where you differentiate n with respect to x. So if these two are equal, then you'd conclude to say what you have here, something like this, is an exact equation. But if this one is not, if these two are not equal, then what you are given is not an exact equation. So from here we also have something like separable equations. Separable. So what you have here as the separable equation. Separable equation are equations such that, let's take for instance you have something like maybe let's say you have y. You have y multiplied by dy has to be equal to x dx, like that. So in this instance, this simply means that you can have some function or a standard equation like this. If you rearrange the standard equation like this, you should be able to have something that looks like this, meaning you can separate the variables where this side you only have those that has y, and then this other side of the equation you have those that have x. Otherwise, if you can't obtain something like this, then the equation that you have is not a separable equation. So this one is some equation that can be separated as the variables, meaning the x on their own, and then also y on its own. So these are a few how you can classify these equations. And then from here, you should be able to first of all express each given equation into a standard form. Then from a standard form, we should be able to say, okay, fine, the given equation, let's say maybe it's a linear, it's a Bernoulli, it's an exact equation, or a separable one. Okay, so basically these are a few things that you should be able to do. So let's look at a few examples concerning these. So under the classification, one of them, or the last one that you'd need to know, is a homogeneous. I almost forgot this one. So homogeneous equations, how are they? So homogeneous equations are equations such that, let's say, given the standard form of an equation. So we said the standard form is something that looks like this. And then for the homogeneous equation, a homogeneous equation is one that, so what you have here is equal to this. So I'm going to write this one as a standard equation. Like this should be equal to the same function, let's say the same function then where x and y are multiplied with some t. So meaning, if you are given some equation like this, if you multiply the t within the x and y, somewhere there you have something like these two should then be equal. Like what you have decided should be equal. Elsewhere, if these two are not equal, then the equation that you are going to have is not a homogeneous equation. And then this is what is used to test for homogeneity. Okay, so then maybe we proceed and look at if there could be any questions that would look at to help us. Alright, so here's another question that we need to work on. So we have to say, determine if what you have here is a homogeneous equation. So basically a few things that you need to remember is the form of a homogeneous equation, the way it looks like, and also you need to know the standard form. So first of all, maybe to start with, let me just write this here. So to start with, you still need to remember the standard form. So this is the standard form. So meaning whatsoever that we have here has to be written in this form. After writing it in this form, then you need to check for homogeneity. So checking for homogeneity is simply saying, okay, fine, if you have a function like this, it's supposed to be y. So if you have a function like this has to be the same as a case where you multiply by a t, where there is x and y. So this is the condition that you need to remember. These are the things that you have to remember. So let's start by first of all expressing what you have here as in standard form. So what you have there is x y squared dx plus, then you have open bracket x squared y plus y squared close dy, then it is equals to 0. So you can express this by maybe first of all, I would say if you divide through, so we're going to have something like dy over dx. So this is what you are expected to have. What is going to happen is that you first of all, you either take this entirely on the other side of the equation so that you remain with this. So I'm going to have this. So this then becomes negative of xy squared dx, like that. So from here you can divide through by this everywhere. So that makes this become dy being equal to xy squared, then divided by what you have here. So this is going to be x squared y plus y squared. So remember, this is a negative like this, and then there's this one where we can say it's dx like that. So after what you have here, if this is okay, you can then divide through by dx, so that our standard form will then be dy dx will then be equal to negative of this divided by x squared y plus y squared. I hope this is visible. So this is what you have as your standard form. So let me clear up some space here. So now what you have here is dy dx is equal to negative of xy squared over x squared y plus y squared. So what you have here is exactly the same as this equation here. So now the first part you are done, you've expressed what you have in the standard form. Then you need to check for homogeneity so that you can conclude whether or not the given equation is a homogeneous equation. So to check for homogeneity, this condition has to be true. So that is to say, what you have here, since this is for homogeneity, you said this is equivalent to that. So what you have here can still be expressed as this, and then it is equal to that. So what you are saying is having this, which is just write it. So this will be written like this, then so this is what you have as dy dx or f of x and y. Then this has to be equal to, when you multiply by t, everywhere there's x and y like that. So multiplying by t, it means that this will be multiplied by t by t by t by t, implying that what we are going to have will then be negative of t of x here times, so this becomes like this, since y is squared, and then you divide, wherever there's x now, we are saying is t of x, then this is squared, also this one will be t y, this one, then you're saying plus. So since this one is also squared, you're going to have t y squared like that. So this is what we have. Now we need to check whether this will then be equivalent to what you have there. If it's not, then we can make a conclusion on this one. So we are saying this is equal to, can have it negative tx, distributing the 2 there, this will be t squared y squared d divided by t squared here, and the x squared t y plus t squared y squared like this. So this is what you have. Then if there's a t, 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 you can factor out a t and see what we remain with. So now factoring out a t here, it leaves us with, we're saying if we factor out a t, we're going to have negative x. Then since there are 2 of the t's here, we're going to have one of them like this. Then the denominator can also factor out a t here. This leaves us with a t x squared, and then y plus, so since we've already factored out one of the t's, we only remain with a t and then a y squared like that. Okay, so at this stage, this and that, they can cancel such that so we are then going to have something like negative xt y squared divided by, so this will be t x squared y plus t, then you have y squared. So now what you have here is it equivalent to the original function, the original equation, this one, which is negative x y squared divided by x squared y plus y squared. So clearly you can see that these two equations are not equal. So you're saying what you have here is not equivalent to that, or checking for this condition hasn't been satisfied, meaning what you had here initially, which is this, is then not equal to what you have here, which is this. So you're saying these two are not equal, so therefore you can say the equation is not a homogeneous equation. Alright, so after having classified or looked at some of the how equations can be classified, so here are a few work that we can look at before we proceed. So we're taught to say write the following equations in standard form. So the standard form of the writing of a standard form is dy dx should be equal to some function of x and y like this. So meaning what you have here, you should be able to manipulate to this format. So maybe we'll start with the first one. We say solution. So the first one, we're saying what you have is x dy dx like this minus y squared is equals to 0. So writing this, already you have dy dx here. So I think we can just go straight and writing our dy dx, and then this y squared can then be put on the other side of the equation. And then the x here, to get rid of this x, you can just divide through by x. That gives us y squared divided by x. So therefore we've written the first equation as in standard form. And then the second one here, which is e to the x dy dx plus e 2x to the 2x, then y being equal to sine of x. Writing this as a standard equation, already you have dy dx. So here what you're doing is as good as solving for dy dx. So you're saying dy dx has to equal to, so already I've sine on the other side of the equation. Then this one, as it is, can be taken on the other side of the equation. What you have is sine of x. Then this one becomes minus e to the 2x or like y like this. And then to get rid of the e to the x here, it's as good as dividing through by e to the x. So this gives us e to the x. And then if you do the same here, e to the x, you're then going to have something like dy dx being equal to, so what you have here can then be written as something like e to the negative x sine of x minus, so this one will cancel with one of them there. Then you're only going to have e x y. So this is the way you write an equation in standard form. This is the standard form of any differential equation like that. Okay, so from here let us proceed and see other things that we can look at on differential equation. So basically this is how one would work out on expressing it as a differential equation. Alright, so this is just a few differential equations. Then here you just need to determine whether or not the following equations are linear equations. So the first thing that you need to know is understanding how a linear equation looks like. So we said a linear equation is one that looks like dy dx, which plus p of x multiplied by y being equal to q of x. So this is the standard. I mean, this is how a linear equation looks like. So you need to determine from all the given equations whether or not these are linear equations. So we'll start with the first one. So the first one, what you have here, y prime. So y prime is another notation of dy dx, or the first derivative like that. So meaning what you have here is that you already have y prime, or dy dx is here. So we can just write this as dy dx. And then we need to have some function p of x. So the function p of x, what you have here, sine of x, can then be written as sine of x like that. Then p of x is multiplied by y. So we have a y here. So this one can then be written like this. And then this is equated. So do something. So this is equated to another function q of x. So what you have here is another function of x. So therefore the first one is a linear equation. So that's how basically you can tell or determine to say whether or not is a linear equation. So we go to the second one. So the second one, already you have dy dx here, and then minus. So we're saying, okay, fine, what you have here can be written as minus x sine of y. Then this can then equal to negative e to the x. So how do you conclude? Is this what you have here? Is it linear? So the answer is not. So we're saying it's not linear. The reasons are, what you have already, you have dy dx as it is supposed to be there, and then here of course you have a function of x. So what you have here, negative x, is a function of x, but the function of x itself has to multiply by y, of which what you have here is not y, rather this is a function of y. So therefore this one cannot be classified as a linear equation like that. So that's how you would tell. So this one is not a linear equation because of this. Okay, so then we come to this one. Is this a linear equation? Is it a linear or not? So already you have dy dx, and then do we have the function p of x here? Do you have the function p of x? Not really. Do we have a y multiplying to it? Not really. Then do we have another function q of x? It's not there. So therefore this one also is not a linear equation. So this is how we tell. So just inspect to say whether all these things are there on the given equation. Then this other one also, we have dy dx like this. And then we have, so this one can then be written as negative x. Then okay, fine. So what you have is dy dx as it's supposed to be there. And then we have some function p of x, which is this one, or this one I would say. And then do we have a y multiplying to this function? We don't have it. So here we don't have a y. And then also if you equate this to a function maybe q of x, so already what you have, we need to have something like q of x, of which this one also is not a linear equation. Basically, for you to have a linear equation, you need to have all these satisfied in the equation like that. Okay, so let's proceed and see other problems.
Nani
Okay, so let us look at something that has to do with the exact differential equations. So the first thing that we need to do, we need to understand what an exact differential equation is. So from the classifications, we know to say, or remember how you can tell to say the given equation is an exact or not. So we have to say determine whether the differential equation that is here 2xy dx plus 1 plus x squared in the brackets dy equal to 0 is exact. So the first thing that you need to check is identify m of x of y and also n of x of y from the given differential equation. So what you're saying here is that m of x of y is what you have this side. So therefore, I can simply say m of x of y is equal to 2xy, like this, and then n of x of y is equal to what you have here in the brackets, like this. Okay, so this is what you have. This is from the classifications. So from here, to check whether or not the given equation is an exact, we take the partials of m with respect to y should be equal to the partial of n with respect to x. So now, taking the partial derivatives here for this one, so taking the partial derivative of m with respect to y is as good as having, so we are saying m, as good as saying m like this. So differentiate this with respect to y, you remain with the 2x. Okay, so again, try to differentiate this one with respect to x. So, I mean, you differentiate this one with respect to x. Differentiating this one with respect to x gives us 2x. So, we can therefore conclude to say the equation is an exact equation. Basically, this is how you would inspect to check whether or not the given equation is an exact differential equation. So let's look at another example similar to this one. So let me just do this. So look at another example that may be of use. So also this one can be checked in a similar manner. So we just need to identify the m of x of y and also the n of x of y. And then from here, take the partial. So already what you have here, this is m of x of y and also this is n of x of y. And then from here, we should be able to take the partial. So we are taking the partial of m with respect to y. So what do you get when you differentiate this one with respect to y? So you treat x as a constant, or you ignore it in other words. So ignoring this one, then you have something like cos, you're saying cos of y. Now, is this equal to when you differentiate this one with respect to x? So differentiating this one with respect to x, only concentrate on this part here, such that you only your interest is on x. So differentiate x. Differentiating x as it is, it will just be a 1 times what you have here. So it's as good as having, it's as good as having what you have here, such that now you're saying this is then equal to. So from here you can make a conclusion to say, therefore, the equation is exact. Determine the function g of x of y that satisfies the differential equation here. So what you have here is an exact differential equation. So maybe from here, you need first of all to check whether or not this differential equation is exact. Then after concluding that, so checking for whether the differential equation is exact, we say partial of m with respect to y should be equal to partial of n with respect to x, which is, so this is m of x of y. So if you differentiate this one with respect to x, you're only going to have 2x. And also if this is n of x of y, so if you differentiate this one with respect to x, then it will be just 2x like that. So these two, what you have here is an exact equation. Okay, fine. Now since we've checked to say the equation is exact, we are then now going to solve or to determine the function g of x of y that satisfies this. So what you have here, g of x of y, will then be a solution to this equation. Okay, so meaning, in other words, you are then saying g of x of y is as a result of m of x of y plus n of x of y, such that you'd need to integrate, or meaning to obtain g, you need to integrate this and also that in order to obtain g. So therefore, in order for us to determine, to find g, we are saying first of all you need to integrate this one with respect to x, and then also integrate this one with respect to y. That's to say, we're saying integrating. So what you have here, this is so m like this. So this this one is integrated, which is equal to 2xy dx, and also we need to integrate this part here with respect to y in order to obtain g. So therefore we are then saying what I have here, we only leaves us with the m like that, which is then going to be equal to, or in other words, instead of having an m here, we are saying, okay, fine, let's have g, because it's g, the function is g. So we differentiated g to obtain this. So integrating g, we're going to have something like, here we're only going to have g of x of y like this being equal to, so this one integrated with respect to x, it is going to be such that we're going to have x squared y, then we're saying plus. So now, since this was just partially integrated, so we're saying there's still other part of y that we can just call, let's just call it h of y, then plus a constant or an a constant of integration. So what you have here, then you need also to say, fine, we're saying plus of this part, which is 1 plus x squared. So this one is with respect to y. So what you need to do now at this point again, we're then going to have what you already have here, you add this part here. So adding this part is as good as saying, okay, fine, what you have is already x squared y plus, so what is going to come here is this part here, which is then in this instance, what you have here is dy. So integrating this as it is here, it only gives us a y plus c, we're saying a squared y, then plus c, the constant like this. So meaning you are then going to add these two. So you're adding this with what you have there, so which is y plus x squared y plus ac. And then if you look closely, what you have here is the same as that one. So meaning this part is already here. So I'm just going to write this. You write a y, this y. So this one is the same as what you have there. Then plus a constant like this. So basically this is what you are going to get as g of x of y. So g of x of y, it is this function that was integrated to obtain this and that. Okay, so we look at a similar example to this one. So let's suppose you have a function x sine of y dx plus, then we say x cos y, maybe we say minus 2y dy. Also we need to find the solution to this one. So the same steps that we've done, we said, okay, fine, the first thing you need to check or verify whether or not this equation is exact. So this is m of x of y. So this one with respect to y, you are just going to have cos of y. Now, is this equal when you differentiate what you have here with the respect to x? So as now saying, is this equal? So differentiate this one with respect to x, this will just be a 1, then you end up with the cos of x. So therefore, what you have here is exact, or the equation is an exact equation. So now from here, then we can then proceed to determining or finding the solution to this equation. So the same thing applies to say, okay, fine, to find the solution is as a result of the partial differentiation of this one and also that one. So we are then saying okay, so the x, and also would need to do the same, or we'll come back to this. So here we only end up with the g of x of y being equal to, so this will then be x squared plus, so we're saying x then sine y like this. Then you're saying plus the constant. So this one, so since this is partially, we're integrating g partially. So we've only integrated this one with respect to x. So we are leaving out this one for y. So therefore, to find the other part should be as something like g of y being equal to, now integrating this part, which is then sine cos of y minus 2x dy. So if we integrate, this is then going to be g of x of y being equal to, so what you have here, it is such that already what you obtain, g of x is the same as g of x, which is then equal to this part here. So that's why we proceed by writing as it is as g of x of y being equal to, so you start writing with what you already have like this. Like that. And then at this point now we would need these. How do we obtain these? Obtain these by integrating this one. So we're then saying, we're therefore saying this would be saying it's negative x, and then this becomes sine of y, and then this will just be negative 2x y like that. So we are then adding this to what you already have. So at this point you then have something like so what you have here is the exact thing that is, except that is a negative. So this one will go with a negative as it is like this. So this is what will be there, and then you're saying minus 2x y, and then you say plus a constant of integration. So therefore this is how you would find the solution to each or any given equation, the first thing that you need to do is to verify whether or not the given equation is exact. Then from there, you proceed by taking the partial, you integrate it partially with respect to x, and then you also go to integrating it with respect to y, and then you have to add the two so that you get your solution. So basically this is how you would go about it. Okay.